use Lysol, we use iodine, isopropyl alcohol, and bleach. You need to know what is the mode of action of each of those disinfectants or antiseptics. So for instance, Lysol is a disinfectant, right? So with that being said, you also need to know the difference between a disinfectant and an antiseptic. Disinfectant is used on non-living surfaces, right? So it's what you guys use every day when you leave, what you should be doing every day when you leave lab, spraying down the tables, right? Lysol. Again, you wouldn't spray, when you leave lab, you wash your hands, you don't spray down yourself with that Lysol mix at your table, okay? Antiseptics are used on living surfaces, on living things. So your antibacterial soap that you wash your hands with before you leave. Your gels, right? Your antibacterial gels, those are antiseptics. So you need to know the difference between them. You also need to know what a zone of inhibition is. So zone of inhibition is a clearing where there's no growth of the bacteria. Okay, so you saw this with some of the disinfectants and antiseptics that you use. Right, it's an area in which there's no growth of the organism. So telling us it was effective, right, against particular organisms, showed us the effectiveness of these disinfectants or antiseptics. You also need to know things that are going to affect just how well these disinfectants or antiseptics work. Well, how much are we using? What's the concentration of these antiseptics or disinfectants? What type of bacteria or microorganism are we trying to get rid of? You saw when you looked at your plates, right? Maybe bleach was effective against Staph aureus, but it wasn't effective against Pseudomonas. Or your Lysol was effective against E. coli, but it wasn't effective against, Pseudomonas or E. coli or Staph aureus, right? Each one of these disinfectants and antiseptics is going to have a specific organism or specific range of action, okay? Also, environmental factors, so pH, temperature, what's the surface that we're trying to disinfect, right? That all plays a role in how well these guys work. Then we get your chemotherapeutic agents. So just like you guys had to know what Lysol does, what iodine does, you need to know what the antibiotics that we tested do. Right, so I'm not going to make you know that entire chart of antibiotics, just those 4 that we worked on. Right, so chloramphenicol, for instance, loves binding to bacterial ribosomes. When it does so, it prevents peptide bond formation. So you inhibit protein synthesis. Some of them inhibit cell wall synthesis. Right, so they're all different in terms of their modes of action. So you need to know that. You also need to know we use Mueller-Hinton agar. So it's a specific, not your basic nutrient agar, it's a different media with a set pH of about 7.2 to 7.4, right? Simply because of the fact that it allows for the diffusion of the antibiotic. Mueller-Hinton, right? Mueller-Hinton agar, again, allows for the diffusion of these antibiotics. Then our transformation lab. So we worked with the P-Glow plasmid. We were looking at 3 genes of interest that we inserted into E. coli. We had GFP, which was your green fluorescent protein, beta-lactamase Z, which did what? Nobody knows? No? I know it's been a while, but if I told you I would give you a beer, somebody would be Ryan. Ryan.
Nah, think about it.
Antibiotic resistance, right? So it gives antibiotic resistance. Then we have arabinose C. What did arabinose C do? It only did it on one plate. Your LB-AMP-ARA. What did it do? Yeah, it turned on, right, the gene or allowed for gene expression of GFP in the presence of arabinose. We worked with E. coli K12. That was a specific strain that we worked with for transformation, okay? Well, what is transformation? It's the process in which a bacteria uptakes a piece of foreign DNA. Generally, it's a circular piece of DNA in the form of a plasmid. Not essential for its survival, right? But it does use it for its own benefit, okay? You also need to know that GFP is extracted from a jellyfish. That's a particular protein from jellyfish. Heat shock and calcium chloride were ways to ease the facilitation, right? To make it easier for E. coli to pick up this plasmid, right? So the calcium chloride, what it does was help to neutralize the charge of the DNA, okay, of E. coli. The heat shock increased the fluidity of the membrane of the bacteria, right? So again, both of these contributing to the, the ease of the uptake of the plasmid, okay? Then we get DNA fingerprinting, or CSI, or crime scene lab. So you need to know areas in which DNA can be obtained. And so bodily fluids, teeth, hair, epithelial cells, right? Those are things that are collected at the crime scene to, extract the DNA from. You also need to know what STRs are. So what are those? Short tandem repeats. Why do we use short tandem repeats?
They're unique.
Specific of DNA, right? It's unique, right? Everybody's different. We all have different STRs, right? Some may have one that looks one way and it be 6 STRs. Somebody else may have 18, right? Versus looking at the entire DNA of a human, because we all have the same genes, right? So we want to focus in on these regions that don't code for anything, right? Polymerase chain reaction, so you need to know, right? That's a method of amplifying or making copies of the DNA, right? Or a segment of DNA. You need to know denaturation, first step. Right? Then we get, of course, the annealing. And so primers recognize bind. Then we get the addition of those dNTPs, or those nucleotides, right? In the extension or elongation phase of PCR, right? Gel electrophoresis, used to, or is an electrical current that's used to separate DNA based upon the differences in the sizes, right? So DNA is negatively charged, it moves, right, across that gel to the positive end, okay, of the electrode, right? Then we get your ELISA. So the ELISA, enzyme-linked immunosorbent assay, we use the indirect method to test for antibodies, right? Antibody production against a particular antigen. Well, we added an antigen to those wells because the whole purpose was to see if, when we test this patient's serum, do we get the production of the antibodies, right? It's seeing, if it's seeing, right, this antigen, then you should get the production of these antibodies to mark these antigens for destruction. Well, why is it called enzyme linked, right? Well, your secondary antibody that you added had horseradish peroxidase enzyme linked to it. Right, well, what did that do? It helped to oxidize the substrate so that we can get a color change, right, and be able to detect a positive versus a negative, which I know it didn't work well for you guys, but I promise it worked in my intro micro classes. Ashley can attest for that.
It did.
Perfect results, okay? Right, so you need to know that. You also need to know that the substrate that we added at the very end, right, the reason that we added is so that we can get that chemical reaction to take place. We can get the oxidation of the substrate to allow for the detection of a positive result. Okay? Then we get, last but not least, your food microbiology. You need to be able to understand